So we were here, we left off with the Hilbert scheme. Hilbert scheme is parameterizing subschemes in a variety. We know that these subschemes, I mean, there is always, in the first pages of Artan tell you there is a bijective correspondence between the structure algebra of a subscheme and the subscheme itself, or a structure sheaf of a subscheme itself. So normally, if you give me some subscheme of an ambient variety X, we call it Z. For the time being, we think of Z being curve, but it doesn't need to be. It sits in this short exact sequence, canonical short exact sequence, and this is the structure sheaf of Z. We discussed that the Hilbert scheme of curves, for instance, due to this phenomena of embedded points, does not necessarily parameterize naked curves, but it parameterizes configurations of naked curves together with fattest structure or reduced structure, scheme theoretic reduced structure, and non-reduced and non-reduced and reducible scheme structure. And then those are these points that roam around. You can think about them as points on the curve or off the curve. Okay, so this is what so far we have done. And so let's us now discuss deformation theory of these things. Deformation theory on Hilbert schemes. On Hilbert schemes. Okay. So the standard deformation theory, deformation theory of subschemes is not well behaved. Is not well behaved, unlike stable maps. That they had a well-behaved deformation obstruction theory. This one does. So what does the Hilbert scheme do? So Hilbert scheme, we discussed it. So we notationally, we had Hilbert scheme of the structure sheaf of varieties, or Hilbert scheme of subschemes of the ambient space, which was the set of isomorphism classes of subscheme Z inside X, such that there is a short canonical exact sequence sitting exactly like this, O of Z, like that, and the Euler characteristic of O of Z is equal to chi, and the Chern class of the Z itself is equal to beta. Homology class of Z is equal to beta. Okay, so that's what it is. And this is a moduli scheme, and it represents a moduli functor. Every time that, so there is I can call this thing moduli functor, like this. It's something from category of schemes over C to groups, if you like. Groups. Yes. And basically, as soon as you give me one of these things, X and then over S, it gives me an S family of Z in X with those properties. So we discussed that in order to discuss deformation theory, I need to perturb underlying the space, because the moduli functor essentially, if I give S as a point, it gives a point, it gives me one of these Z in X's. If I give it as some scheme S, it gives me a one-dimensional, or whatever dimension of the scheme S is, family on the moduli space. So if I deform if I give it a point and I deform that point, make it fat, it gives me some infinitesimal neighborhood in the actual moduli space to me. If I give it a family, and if I extend this family S, the parameterizing scheme, into S prime, it basically gives me a notion of deformation of S family to S prime family. So that's basically what it does. Okay, so, and so in order to get these flat deformations, there are abstractions. So such that deformations and obstructions to extend an S family of Z in X to an S prime family of Z in X with such and such properties lives in, so the deformation obstructions are given by groups, given by the following groups. So the deformation, so essentially best way of actually looking at this thing is that we know that the Hilbert scheme is parameterizing basically configurations like that. So we know that it is like this. So O of Z is always a quotient of O of X. So it's parameterizing such OZs, which are both quotient of O of X, and the kernel is the ideal sheaf of that subscheme. If you study literature on the Hilbert scheme, you can actually see that deformation space of this thing captured by the following groups. So deformations are captured by homomorphisms from I Z of X to O of Z. Okay, all possible deformations, and the obstructions are given by X1 I Z to O of Z. Okay, and this is actually tensored with, so this is tensored with some J, ideal J, and this is also tensored with ideal J. And what is J? J is the nilpotent, the kernel of the nilpotent extension of S into S prime. So if you have this thing, you have O of S prime, and you have O of S, and there is an ideal associated to this thing. This is something we discussed. As soon as you get this thing and you fatten S into S prime, structure sheaf of S prime surjects onto O of S. Associated to that fattening, there is an ideal of this deformation, and then these groups, the way that the family deforms, the possible set of deformations sits in a vector space. That vector space is an element of, is basically this homomorphism space from kernel to quotient, co-kernel. And the X1s are obstructions. So this is the deformations and these are the obstructions. Okay. Now, the problem is that, the issue is that the higher obstructions do not vanish, do not necessarily vanish. Maybe sometimes they vanish, but not here. Necessarily vanish. That is, we have higher order obstructions, higher order obstructions to obstructions, for instance, higher order obstructions given by higher X groups, groups. And what are those things? These are, for instance, X2 I, the kernel, to quotient. You see, this is not necessarily vanishing. And because it doesn't vanish, the deformation obstruction complex will have cohomologies more than 2. non-trivial cohomology is more than 2. So it's not going to be a 2-term perfect complex. Okay, so there is no well-defined deformation obstruction theory for Hilbert scheme. Hence, there doesn't exist well-defined deformation obstruction theory for Hilbert scheme. And no well-defined expected dimension. So similarly, no well-defined expected dimension, and no virtual class. And finally, no well-defined virtual fundamental class. And this is an issue. Okay, this is a big issue. So what should we do? In order to remedy this issue, we are going to replace the Hilbert scheme itself with a different moduli space. In order to remedy this issue, we will consider the moduli space I chi x beta parameterizing pairs E and phi such that 1. E is a torsion-free sheaf on X, torsion-free sheaf on X such that rank of E is equal to 1, 2. E is equipped with a trivialization, This is a phi, which is a map from determinant of the sheaf to O of X. And this map is an isomorphism. What is the determinant of the sheaf? Determinant of a bundle, we know what it is, but determinant of the sheaf is basically that if you have this sheaf and then you can find some locally free resolution of it, R0, R1, and it keeps going. And over a projective variety, your hope and a smooth, this locally free resolution stops at some point like this. And then you basically take an alternating sum of lambda exterior algebras of these things. Alternating sum. So you get take exterior algebra of this times exterior algebra n-1 of R-1, and it keeps going. R0. Okay. And so basically you dualize it. So you take this one, next term is lambda 2 of R1. You dualize it, and then dualize, don't dualize, and it keeps going like that, alternatingly. And this is the determinant of this sheaf. Okay, and okay, it's a line bundle. Determinant of the sheaf is a line bundle, and we would like to consider a moduli space where our sheaves are torsion-free rank 1, and determinant that is a line bundle is O. 3, numerical invariants of E are given by second Chern class of E equal to minus beta, and Euler characteristic of E is equal to Euler characteristic of O of X minus this Euler characteristic that we had before. So, all right, what is the point? The point is the following. Why is it that we are studying such moduli space? It is because this is a general construction. You're studying all such torsion-free sheaves, but in particular, those sheaves which are ideal sheaves of some subscheme Z inside X, exactly are our coherent sheaves. E. They are torsion-free. Their rank is 1. Ideal sheaf is always rank 1. Their determinant is O. Yes. And their Chern classes are also this way. So let's just see. So let's see if this is the case. Example. I for given Z inside X such that Euler characteristic of O of Z is equal to chi and homology class of Z is equal to beta, I of Z in X is satisfying properties of E. Is that true? Well, yes, it's true because first of all, rank of IZX is equal to 1. Determinant of IZX is equal to O of X. That's correct. And then how about the Chern character? So the Chern character situation, so this is correct. This is also correct. Chern character situation, I of Zx sits inside an exact sequence like that. From here, by the property of the Chern character, we can actually see that the Chern character of I Zx is the Chern character of the middle term minus Chern character of the last term over here. Chern character of the last term over here, we can calculate. This is some sheaf, so you have this, and you have Z, and this is X. This is some sheaf whose Euler characteristic, so okay, so you can pick any ambient variety that you want. Let us assume that dimension of X over C is equal to N. Chern character of O of Z, because it's supported only on the curve, is 0, 0. So 0 Chern character is 0. This is rank of the sheaf. First Chern character, second Chern character. Z is a one complex dimensional subscheme. So the first time that you will see a non-zero number here is the last, 1 to the last. So 1 to the last is going to be class of OZ. So that is actually beta. And then last one, Chern N of OZ is exactly Euler characteristic of OZ, and that's going to be chi. Okay, so this is what it is. How about Chern character of O? Chern character of O is different. It's always supported everywhere. Its rank is 1. It doesn't have anything else. And then it just goes to the very end, and you will see Chern of O of X. Okay, so these are like two vectors. Chern of IZX is the tuple this minus the tuple 0, 0, then maybe here beta, and then Chern of OZ, which is actually equal to this one. So if you calculate, you will see that Chern of IZ of X is 1, 0, 0, 0 minus beta minus chi. It's a vector. So this is n by 1 vector as an n tuple. Okay, so indeed it is true that the moduli space that parameterizes torsion-free sheaves of rank 1 in this ambient variety of dimension n does parameterize ideal sheaves of curves in this ambient variety. Those are a particular type of such sheaves. Yes, so that's good. So, all right. So what is the point though? So this moduli space actually parameterizes such sheaves, and so if I have, so it is parameterizing these sheaves E, that's the way that we defined, but then in particular, the set of isomorphism classes of ideal sheaves of subschemes is actually subset of, so these are isom classes, subset of this moduli space. And in fact, here is a theorem that says the only possible, there is, one can show that the only possibility for E is to be ideal sheaves, which actually implies that this thing is actually an equality. So this is the moduli space. So the Hilbert scheme parameterizes quotients like that, and the moduli space of ideal sheaves parameterizes I of Zx. So the information of the Hilbert scheme is the information of the quotient. Of course, I of Z in X sits inside as the kernel, but the Hilbert scheme essentially has a different structure than just sheaves, you see? So that I can just study a priori rank 1 sheaves. I don't need them to be necessarily kernel of something, okay? All right, so these two moduli spaces are parameterizing different things. Nevertheless, if you parameterize ideal sheaves, you have parameterized the ambient, the subscheme of X sitting in X, right? So this is why studying this moduli space I instead of Hilbert scheme is useful. Now, here is the thing. There is the natural map. The natural map. The natural map from Hilbert scheme. X beta to ideal moduli space of ideal sheaves X beta, which takes Hilbert scheme parameterizes subschemes, and this is the one parameterizing ideal sheaf of the subscheme. This is the natural map, is an isomorphism in the level of closed points. Okay, that's exactly what we were saying. So let us see the proof of this statement. We see the proof of this statement is as follows. Any questions so far? Okay. By the way, let me see. Just quickly switching back to Zoom environment. Let's see who are the people. Ji-Chang is here. Eno is here as well. Welcome, guys. Okay. Okay. So here is the proof. So given a coherent sheaf, E, an element of this moduli space, rank 1 torsion free with those numerical invariants. What we can do is, in order to show that these two moduli spaces are related to each other, you need to start from E and end up with the ideal sheaf, right? With the subscheme, right? So how do you do that? This is the procedure. You can take the double dual of E. So the double dual of E is given by. What is the double dual? So remark, the double dual given a coherent sheaf with support in ambient variety X of codimension C, the double dual, of E is given by XC. You take the dual twice. The dual of the dual. So you take the XC of E with respect to O of X. That's a sheaf. Which X group? This is an X sheaf. X sheaf. Yes. Which is it? Which X group is it? Well, the one whose order of self-extensions or order of extensions is C, the codimension of E. And then you take the dual again. That's what double dual is. Okay, this definition of double dual, and it's written this way. Okay, so now let us try it. So if I take E for E in this moduli space, all I need to know is what is codimension of support of coherent sheaves. Coherent sheaves are torsion free. Torsion free means they are supported everywhere. So codimension of support of E is going to be equal to 0. So if I pick such E, the double dual of E, so for E in this moduli space, double dual of E then is going to be by definition X0 of X0 of E, OX, comma OX. It's a very nice object. Okay. This is what is called reflexive sheaf. So this is a reflexive sheaf of rank 1 with trivial determinant. Okay. In order to see what this is, I suggest you the following. Look at the book Geometry of Moduli Spaces of Sheaves by Daniel Hoybrechts, who is in Bonn. Look at this book, and you can see what a reflexive sheaf is, and this double dual is also explained over there. Okay, when you take the double dual, there is a fact that taking the double dual allows you to embed E inside this double dual. So the fact is that E embeds in its double dual, always. So something like that. Now, the point is that because this guy, this double dual is reflexive sheaf of rank 1 with trivial determinant, it must be that the double dual is isomorphic to OX. There is no other way. You have a reflexive sheaf, and reflexive means reflexive sheaf given here, given G being reflexive, G is reflexive, G, a coherent sheaf, G is reflexive if G is isomorphic to G double dual. That's what reflexive means. Okay? Turns out that E double dual, okay, is reflexive. So E double dual is isomorphic to E double dual. When it is reflexive of rank 1 with trivial determinant, then it's got to be O. So E double dual turns out to be O. Okay. It's a sheaf of rank 1 with trivial determinant, and it can, and so E double dual is isomorphic to O of X. The fact is that E embeds in its double dual, so E embeds inside O. Hence, we see immediately that when E becomes a subsheaf of O, it's immediately seen that it's an ideal sheaf of a subscheme. So we immediately see that we can realize this sheaf E as ideal sheaf of a subscheme Z inside X. Okay, so therefore we can actually see that E is realized as ideal sheaf of some subscheme, and what completes this diagram is O structure sheaf of that size subscheme. This is why in the level of closed points in the moduli space, there's a one-to-one bijective map between Hilbert's scheme and this moduli space of sheaves. You see, as soon as you give me one of these sheaves E, I can take the double dual, it embeds inside E double dual, and it produces the quotient. As soon as I get this quotient, this is something that is in the Hilbert scheme. Therefore, I can immediately bijectively map myself to Hilbert scheme. Okay, so, but this is good, while underlying subscheme Z associated to ideal sheaf of Z inside X are the same as before, same as in Hilbert's scheme. The deformation obstruction for torsion for the obstruction spaces for torsion-free sheaves with trivialized determinant are different. from the case of Hilbert scheme, from the case of Hilbert scheme. And this is a very important fact. Okay. So let us make an example. So here is an example. When complex dimension of x is equal to 3. Oops. Sorry. Give me a second, guys. Let me pick this one up very quickly. Sorry, guys. Okay. When the dimension of x over complex numbers is 3, I would like to show you what the deformation obstruction theory looks like. We have seen this phenomena before. In general, for sheaf moduli spaces, the deformations are given by x1, let's say, given over a point, let's say I pick a point in the moduli space. This is the sheaf moduli space, x1 e e. And the obstructions are x2 e e again. Okay. And then if the dimension of the ambient variety is 3, there is x3 e comma e, and then there is homomorphisms or automorphisms of these sheaves, which is hom e e. Okay. All right, so now you might say this is a lot of trouble because our deformation obstruction complex has 4 terms. What should I do with this? Here is the fact. The fact that actually immediately gives you what you want is the very particular characteristics of these sheaves. The moduli space I satisfies, parameterizes sheaves whose determinant is O. There is a choice of trivialization. There is in fact a map. So if I have, so I'm going to come back to this 1, 2, 3, 4 term complex. But I'm going to first show you what this moduli space is. If I have the moduli space of coherent sheaves, and I've picked one coherent sheaf, there is a map from this moduli space to the Picard variety or Picard scheme of ambient variety X. It parameterizes line bundles on X. That's what the Picard scheme or Picard variety does. Claim is there is a map from moduli space of coherent sheaves on X, E in coherent sheaves on X, to this Picard variety. And what is that map? It's the map that takes E to the determinant of that sheaf. Determinant of a sheaf is a line bundle. So as soon as you give me a coherent sheaf, I find a locally free resolution of it. I take an alternating tensor product of the exterior algebras of all the terms in that resolution. I get a line bundle. So that's my line bundle L. Now, as you can see, we are looking at a particular sublocus of this moduli space. We are looking at not all sheaves, but the sheaves whose line bundle, determinant line bundle is fixed. So here it is. We have some particular line bundle here, and this line bundle is O of X. there is always this this sheaf map, this determinant map. So the determinant map takes me from the moduli space of coherent sheaves to Picard variety of X. So I take the O of X in here, and then let's call this map something, maybe det, determinant. And I will be looking at those sheaves in the moduli space of coherent sheaves whose determinant is trivial, right? So I can look at det inverse, the map, a pre-image under the determinant map of O of X. And this thing sits inside here. In particular, det inverse of O of X parameterizes E in coherent sheaves on X such that determinant of E is exactly equal to O of X. But that's exactly the moduli space we are interested in. So our moduli space, when I look at sublocus in here, our moduli space lies inside here. Okay, what is the advantage of knowing this fact? The advantage is that not only there is map between these two moduli spaces, there is also map between their deformation spaces. So if this map is det, then there is a map I can call tangent of det, which is taking me from tangent space of moduli space of E to the tangent of the Picard variety of X. All right. So then, if I want to discuss tangent space of I of X, I of chi X beta, that's the pre-image tangent under the tangent determinant of O of X. Okay, or maybe I am writing it wrongly, a little bit notationally wrong, not wrong, but notationally wrong. I can look at O of X and then ask myself, what is tangent space to the Picard scheme of X at that point? Again, Picard scheme is parameterizing sheaves, except that these sheaves are line bundles on X. Deformation of this thing, which is the tangent space, is given by X1 E comma E, which is O comma O. So in fact, if I want to look at the tangents, I would look at the pre-image under this tangent map of X1 O comma O, right? That's what it is. And that sits inside here. Okay, so that is not bad. Let us actually write down, pick a point, sheaf E, write down this one and write down this one, and basically see what is the fiber parameterized by, because we are looking at the fiber over the tangent space on the Picard variety of X. So there is a map from M of E to Picard variety of X. There is a map from tangent scheme of M of E to the tangent scheme of Picard variety of X. And if I pick a point E, there is a map from tangent to space at that point to the tangent space on the Picard variety of X, but the image of E inside Picard variety of X is O. So that's X1, O of X, O of X. It's correct, and this is the determinant map. But then Grothendieck tells you taking extensions of O with respect to itself is the same as H1 of O of X, first cohomology, over X. This is the same. So, okay, there is a surjective map because this map is surjective, projection map. So there is a surjective map to here. And this map has a kernel. And that kernel is called trace-free extension group. And is denoted by XI E comma E trace-free. You put it in here. And in fact, it sits inside X1 E comma E and then H1 of XOX. Not all extensions of E comma E are trace-free. This is the trace map. It's also called the trace map. It's the map that takes X1 E comma E to this, which is the same as X1 O comma O, which is also the same as X1, if you want to see it better, determinant of E, determinant of E. Because if determinant of E is L, L and L cancel each other and you're just left with O. Got it? Okay, so this is the trace-free map. And this trace-free at a given point is the tangent space at the point E of the moduli space of coherent sheaves on E. And it's just realized at the same time by the tangent space at the point E of the sublocus of the moduli space, which is moduli space of coherent sheaves, which is the same as tangent space at the point E of I comma X beta. As a tangent space, it's just like that. It's the same as space. Okay? So now I'm looking at the deformation theory of Ix comma beta, not the moduli space of all possible coherent sheaves, but the moduli space of coherent sheaves on X whose determinant is fixed. Doesn't matter, by the way, if the determinant is O, even if it is L, same exact story. If this was L, this was X comma LL, but L line bundles are invertible, so they cancel each other. You're still left with H1 of XOX. So this part is exactly going to be the same. So as soon as you're looking at the sublocus of the moduli space of coherent sheaves, for which determinant of E is L, the deformation theory of points on that space is not given by X1 anymore. It's given by trace-free X1. Similarly for obstructions. So in the level of obstructions, there is always a map from X2 EE to X2 determinant of E, which is X2 O, which is H2 XOX. And the kernel of this map is exactly trace-free X2 kernel. Okay? That's how it is. This is the obstructions. So let's go back to deformation obstruction theory of this moduli space. Now I know I'm not looking at X1, X2, X3, but at trace-free ones. So I'm looking at homomorphism E comma E trace-free, X1 E comma E trace-free, X2 E comma E trace-free, X3 E comma E trace-free. I'm going to make an assumption that dimension of X over complex numbers is 3 and X is a Calabi-Yau variety. Later, I will relax this assumption. This is my assumption. But for now, X is Calabi-Yau 3. The point is that if you take these exact sequences, so in this level, this is the one that sits as HOM EE, and then H0XOX, which is 0, which is C. If you have torsion-free sheaf, torsion-free, rank 1, this sheaf is called the stable. And by stability, the homomorphisms, automorphisms of these sheaves are exactly C. Because the trace-free home sits in this exact sequence, and this part is isomorphism, this guy vanishes. So this goes away. Because the dimension of X is 3, and X is assumed to be Calabi-Yau, we know that this is isomorphic to trace-free hom EE dual. So this guy vanishes as well. So as you can see, as soon as you restrict yourself to the moduli space of sheaves with fixed determinant, which are stable because they are torsion-free and rank 1, deformation theory of this moduli space gives you only 2 non-vanishing cohomology classes or cohomology groups. Okay? So by Serre duality, the trace-free X groups vanish in degree 0 and 3. So this approach gives a perfect 2-term deformation obstruction theory. So I showed you this in absolutely elaborative detail because I would like you to understand that how much of a long path it has been to achieve at well-defined obstruction theories for moduli spaces of sheaves. These days, on threefolds, not just Calabi-Yau threefolds, but on threefolds and surfaces even, you can define the notion of Donaldson-Thomas invariants, obstruction theories, expected dimension, and virtual class. But a priori right now, the only thing that you are seeing that is possible to do is to do this over the moduli space of coherent sheaves which are stable. Okay, that's one thing that we know. But sheaves with fixed determinant and on Calabi-Yau 3 varieties. If this X group doesn't vanish, in general, this is dual to this 1 times canonical of X. If the canonical of X is not O, then these two things are not isomorphic to another. So one of them vanishes, HOM vanishes, but X3 doesn't vanish. Okay. And so a priori, you see that this theory is not well defined. We will discuss about that. Okay. So, question. Yeah.
Oh, can I ask questions?
Mm-hmm, mm-hmm.
Yeah, so the deformation here is any relation between the deformation of Calabi-Yau 3 manifold? Because
absolutely, yes.
Okay, so is there any So precise description for this relationship?
The precise description is that, as I said, this is the deformations of complex and Kähler structure of X.
Mm-hmm.
So growth index functorial point of view allows you to look at sheaves on X.
Mm-hmm.
So your moduli space, let's say this I, I'm gonna put it as a curly I. This is a map from, this thing is a map from some category of schemes over complex numbers to sets of, for us, isomorphism classes of these sheaves, E, satisfying all the conditions. The point is that if you pick a scheme to be a point, this gives you one of those sheaves on X. If you pick scheme over complex numbers a line, this gives you a one-dimensional family of those things on X, right? Now, as soon as you pick some scheme S and you parameterize it and you thicken it to S prime, this gives you a deformation of that sheaf on the original variety X, right?
Okay.
So the point is that now you will say, but this is a deformation of the parameterizing scheme, but not X itself.
Yeah.
The point is that I can take X and deform it and make X into some object X prime. Well, of course, this is what we are trying to do, but the way we are formally doing this is that instead of this deformation of X to X prime, I'm thinking of this deformation as a family, as a family of X's.
Okay.
So I'm thinking of this as X times S over S, something like that, over X. If S is a point, I get X back. If S is a fat point, some point like this, I get a fattening of X. If S is a one-dimensional thing, I get a family of X's. If S is a little bit thickening of that one-dimensional thing, I get a thickening of family of X's, and so on. You see? This is so the point is that we are really trying to define invariants associated to deformation of X, really.
Okay. Okay.
So this invariant has a long way to even be defined. You take X, a variety, you deform its complex and Kähler structure. Okay. Then you look at sheaves on this variety. Well, there is a moduli space for it. There's not just one sheaf. There's a moduli space of such things. And then on this moduli space, there are some bundles like deformation and obstruction bundle from which we are going to define an integral and compute an invariant. That's what we are doing.
Okay, thank you.
Sure. But that's a good question. Your question is really that it seems like we are parameterizing this S and thickening S. Where is the thickening of X happening? The thickening of X is exactly this thing I told you. Think about a given variety. So let's say X is quintic threefold given by in P4. So P4 has 5 homogeneous coordinates. So this is quintic threefold. Let's see that. Now I want to deform X. Deform X. Well, I can deform it, no problem. I can do this and then do T here. You see? If I do that, well, of course, this is very similar to realizing X as a family over A1, right? Because this T is an element of A1, for instance. So that's what it is. the parameterization of total space of this family are coordinates that give us X together with the T, and this T belongs to here.
Okay.
But this family is not a trivial family. Okay, so that's how it is.
Okay.
Yeah, and then if I want to take T in A1, then I can thicken A1. So I can look at also x05 plus x15 all the way to x to the 4, 5 T square, you see? Now the point is for every point of A1, if I look at A1, every point of A1 associated to T square is a fat point. So the thing that this belongs to is the fat A1. Of course, topologically, it's isomorphic to A1, but it's really, algebraically, is fattening of A1. It's like a degrees 2 hypersurface, like that. So this is A1 of order 2. So now I have my quintic threefold, and I'm defining some sheaves on it, and I deform it, and then I parameterize it over A1, and I parameterizing over fattening of A1. So this is A1, and this is A1 thickening of A1 of order 2. So this is my S, and this is my S prime. And I'm trying to see, now that I deform my variety this way, how can I see the deformations of sheaves? Okay, so this is what we are doing. Yeah.
And that will lead the deformation for the modular space of a sheaf?
Absolutely. Absolutely.
Yeah. Oh, I see.
Sorry.
Thank you.
Yeah.
So yeah.
Yeah, this is the point of view.
Which property we are using here to rely on the Calabi-Yau threefold?
The property we used here to rely on Calabi-Yau threefold is the fact that when we argued, we wanted to see what happens to this term in here. We said first, if E is a stable object, a stable coherent sheaves, homomorphism from E to itself is isomorphic to C. So that immediately means this exact sequence, this one, which is very important, tells us that, so Richard Thomas was so smart because he realized if we look at sheaves with fixed determinant, then the Hom 0 part vanishes.
Okay.
So this goes away. But then he said, what should I do with X3 then? If X is Calabi-Yau 3, X3 is isomorphic to Hom EE dual. Because the canonical bundle is just O. So because Hom EE is 0, X3 trace 3 is also 0. So for this, we use the Calabi-Yau 3 property.
Oh, we're just using the canonical bundle. It's a trivial.
That's right. That's right. In general, X3 EE, even the trace free part is isomorphic to Hom EE tensor with canonical, right? Dual. Okay, but Hom E comma E tensor canonical is not the same as Hom EE. But if K is equal to O, it is. Then it goes away.
Okay.
Okay. So Calabi-Yau 3 is used here.
So that means we can do some generalization to any perhaps projective varieties with this property.
So if it's just a projective variety
with a trivial canonical bundle, I mean,
well, if the canonical bundle is trivial, it's gonna be a Calabi-Yau.
Yeah.
But if it is just a general projective variety, but not Calabi-Yau, then you need to work hard for it. But that's also been figured out. There's a condition that tells you that if some other property of these sheaves is satisfied, even if the X is not Calabi-Yau 3, you can still have a well-defined deformation obstruction theory. I will discuss that. That's very important.
Okay.
And that's also work of Richard Thomas. Okay. That was absolutely remarkable and beautiful. The second one is the work of Richard Thomas and Daniel Hoybrechts himself, the one who wrote that book. Very beautiful paper.
Okay.
Okay, but we will discuss it.
Thank
Okay,
you.
so for now, we are still, of course, for now, we are in the realm where we are looking at ideal sheaves. E is an ideal sheaf. We proved that because it embeds inside this double dual, rank 1, torsion free. X is assumed to be complex dimension 3 and Calabi-Yau. So everything is just cooked in a way that we want. But okay, this is the easiest case. So let's just see. Then by Serre duality, this approach gives a perfect obstruction theory, very good. And with expected dimension, the perfect obstruction theory here, perfect obstruction theory here is with expected dimension, expected dimension. So what's the expected dimension? We know that it's the expected dimension is this dimension of deformations minus obstructions. So it is the dimension of deformation space with, in this particular case, when we fix the trivial, we fix the determinant, whatever that is, it's going to be trace-free part minus dimension of x2, also trace-free part E comma E. Okay.
Okay.
This is that, and actually, you can see that this from Grothendieck, Riemann-Roch formula. It actually shows that this number is going to be equal to Euler form of E comma E, Euler characteristic of E with respect to E itself, minus Euler characteristic of O of X. Okay.
Okay.
This is basically what it is. And actually, going to be. So let's see. So this is equal to that, and actually, this turns out to be minus canonical bundle, canonical class of X intersected with beta. This is basically what it is. Okay, this is that number.
Okay.
So this means canonical class integrated over beta. This is what it means. All right. So what does this mean? It means that if I could construct a virtual cycle associated to this moduli space, this implies by all the discussions that we had, that the virtual cycle of this moduli space has a degree. Degree of it is equal to either it is degree 0, in which case this means that X is, when this is the situation when X is Calabi-Yau variety, or its degree, it's going to be degree K of X or beta, something like that, otherwise. If K of X is Calabi-Yau, if X is Calabi-Yau, this would be O of X. It's a trivial bundle. Its intersection with homology class beta is going to be 0. So we have discussed intuition about the virtual cycle. So let me remind you, this is a reminder and remark. The realization of the fact that the moduli space of ideal sheaves behaves much better than Hilbert's scheme. Is first of all is in the thesis of Richard Thomas. Beautiful thesis. It's available. I suggest you, if you're interested in this, read it. It's instructive. Okay. And when in the case X is Calabi-Yau 3, virtual dimension, degree of the virtual dimension, which is the degree of the virtual cycle, is equal to 0 because of this formula. What this implies is that I have the moduli space I chi x beta, and I have a well-defined suitable obstruction bundle on it. We had a good discussion about this. And this obstruction bundle has the natural section. And the locus where this section intersects with the moduli space itself, in fact, is zero-dimensional. Okay, so these are actually points. So the locus is points. So this is a point class, this is a point class, and this is a point class. The virtual class of this moduli space is going to be some number times point class. It's a class in homology, Chow homology of the moduli space. And the fact that it's sitting in degree 0 tells you it's nothing but just points. So if I calculate these number of points, then that's the Donaldson-Thomas invariant essentially. Okay. So this is what the Donaldson-Thomas invariant is. Donaldson-Thomas invariant is in fact integral when X is Calabi-Yau 3. Donaldson-Thomas invariant is this integral of I chi x beta virtual class, but because of Calabi-Yau, the virtual dimension is expected dimension is 0. The appropriate cohomology class I will be integrating against this cycle is just the codimension 0 cohomology class, which is a number, constant. Degree 0 cohomology class. Yeah. So that's it. So this is what this notation means. Essentially, integral of 1 means count a 1 in here and a 1 in here and a 1 in here, count them, and the sum of these ones gives you this invariant, n. Okay, so this is what it is. All right. So let me make a connection to Gromov-Witten theory. Here's the second remark. As in Gromov-Witten theory, we have a virtual class with dimension minus k of x times beta. And in Gromov-Witten theory, we saw that the virtual dimension was also minus k of x times beta, independent of number of marked points. And equal to virtual dimension of m bar G0 X beta when X was Calabi-Yau-3. Okay, so this, we had this thing back then also. Okay. All right. So this is what we are doing here. Now, again, since we are making similarities between the Gromov-Witten theory and Donaldson-Thomas theory, let's talk about primary invariants. So this is the situation where we were trying to count curves passing through cycles in the variety. So let us again do the same game. Let's alpha 1 to alpha n be elements of cohomology of X with rational coefficients, be cohomology classes. Cohomology classes dual to collection of topological cycles called cycles Zi in X. Okay, so this is what we had by the expected dimension formula. If sum of the degree of alpha I, we were just discussing this lately, -2 is equal to 2 times minus k of x times beta, then we expect a finite number of curves intersecting these cycles, the ones we call Zi, right? And we constructed an enumerative problem using evaluation maps. So, and we constructed the enumerative Gromov-Witten problem using the evaluation maps. So what did we do? We did have the moduli space of stable maps, M bar G n X beta. We had the evaluation maps to X to the N, and we had the M bar G n, that one. And then we define the integral of the Gromov-Witten class, I n X beta, of alpha 1 to alpha n as integral of the pullback of alpha i's, but cup products with each other. So I from 1 to whatever number of them, k or n, right? Evaluation pullback of alpha I. Yes, and we integrated this thing over the virtual class of mgn x beta virtual, and we knew that these gives us rational numbers, and those are Gromov-Witten numbers. Picture we had with this was we had the X, and we had cycles of different kind, Z1, Z2, Z3, Zn, and enumerative problem was counting curves with n markings on them so that the marked points on curve match exactly, intersect exactly with the cycle Zi's. So the curve goes here, for instance, intersects this one, maybe intersects it again, and again, no problem. It goes here, and so on and so forth. And so we had the mark points, P1, P2, up to Pn that way. This was a nice enumerative problem, and the Gromov-Witten invariant completely was with these primary insertions, and insertions here are alpha i's, was defined as an enumerative invariant. Now, is it true that we can do the same thing in Donaldson-Thomas theory? So in Donaldson-Thomas theory, okay, we have, well, there's a certain issue. We have no evaluation map. We don't, because we are parameterizing sheaf moduli spaces. We have no evaluation maps. However, we can use churn classes of tautological sheaf, the universal sheaf, tautological sheaf of Hilbert scheme, to define DT invariants with primary insertions, alpha i's. So, okay, let me tell you how is this done. So this is the Hilbert scheme, and there's a map to X, right? No, there is no map to X. There is just Hilbert scheme times X. There's a map to X, and that's the projection onto the second factor. I call it pi 2. And then there is the map to Hilbert scheme. So there is the map to Hilbert scheme. And that's what I will call pi 1. So given alpha I in cohomology theory of X, okay, we can define an operator the following way. I'm going to call it sigma 0 of alpha I is going to be pi 1 lower star of something. So I'm going to pull back. It's like a Fourier transform. I'm going to start from some alpha I in here, pull it back up, and then push it forward onto Hilbert. So I'm going to pull it back up. Pull it back up, pi 2 upper star of alpha I, okay? And then I'm going to intersect it with something. This moduli space Hilbert scheme has a universal family. And this universal family is the general ideal sheaf. I'm sorry. You should have told me. So I'm not going to use this because now I have replaced my point of view. Instead of Hilbert scheme, I'm counting moduli space of sheaf. So I called it I chi x beta, I chi x beta. Okay. There is a universal ideal sheaf, or E tilde, sitting in here. So I'm going to take this and then copy it with minus second churn character of E tilde. Okay. And I would like this to be an operator. I would like to intersect this with pi 1 upper star of blank. And what is this operator? So this operator I would like to be sigma 0 of alpha I of blank. And this is a map from homology theory of I chi x beta to homology theory of I chi x beta. So it's basically saying the following. For each one of the choices of alpha i's, I have an operator that takes some homology class here, beta or whatever, some cycle beta, some gamma in here, pull it back up, caps it with pullback of alpha, and then cup everything with the second Chern character of the universal sheaf. Okay? And this is very similar to what we are doing in here, kind of. It's very similar, I mentioned the Fourier transform because the Fourier transforms have a Fourier kernel. The kernel is the thing that is in the integrand. When you take Fourier transform of, so you have two spaces, you always Fourier transform takes you from a space X to a space S, right? What is this Fourier transform? So Fourier transform is a space X to a space S. The way it is that it takes you from X to X times S and then integrates along the fibers and gives you S. That's what the Fourier transform is. So if I give you a function of X in here, Fourier transform is some integral e to the minus S x f of x dx, something like that. So what does this mean? It means that you have taken your function f, pulled it back to this x times s, you have multiplied it by Fourier kernel, and you're integrated along the fiber of x, so the result this produces for you is some function of s. So this is very similar to what we are doing in here. We pull back alpha i's, we cap it with the kernel, but we also want to pull back cohomology or homology classes from this our moduli space over there. And so then integrate along the fibers and get back something in homology theory of I. So if this is the case, then the primary, what is called primary Donaldson-Thomas invariants are defined by the following. So it's alpha 1 to alpha n dt invariants cross beta and m of the degree of the pi k-fold product of sigma 0 alpha k from 1 to n of I x beta virtual. And this is exactly actually equal to what this means is integral of k-fold k product of sigma zeros of alpha k integrated against virtual class. Okay. So this is what it is. Now, you might say, what happened? I have an operator, okay? It takes an element of homology of moduli space of sheaves. And it can produce an element of homology in here, or a number. So, okay, in particular, one of those very useful elements is the virtual class itself. The virtual class of this moduli space is exactly an element in here. So I apply my operator on the virtual class, and I give you a number. So if I take sigma alpha I of something and I put in inside the argument the virtual class of I, then that means that over here I will be putting virtual class. And then if I integrate this, I will get a number. And that number is exactly Donaldson-Thomas invariant with primary insertions alpha 1, alpha n. What does that Donaldson-Thomas invariant mean? Well, it's not so easy to make a sense of it geometrically the same way that we did for curves. Count curves that pass through certain cycles. Well, we can't really do it that way, but there is a good way of relating it to this picture, which I'm going to do next time. Okay? Any questions? If no questions, I think this is a good space, good place to stop.